Welcome back. So in our last video, we talked about intercepts, right? And we use intercepts as kind of a way to show us where can we be grounded in our coordinate plane, right? So where are we grounded in our x-axis? Where are we grounded in our y-axis? But that only paints a partial picture of what our function is going to look like if we were to graph it. And when we are given a function or an equation, we want to make sure that when we look at it, we can kind of intuit what is it really going to look like before I use or rely on technology like my TI-84 or my Decimus calculator, right? And so while the intercepts tell us a lot about where we're grounded in the xy axis, we want to also be looking at degrees and some other features about our actual function that tells us the general shape. And some of the shape patterns that we can rely on require us to look at the degree of our polynomial. So we know that when our degree is even, right? So when the highest exponent of our function is even, it tells us that when the graph of a polynomial function is on the graph, right, the right and left sides have the same behavior. Okay, so what does that really mean? So let's give an example of this. So one of the most classic examples of this could be something like f of x equals x squared. That's a function with the highest degree 2 being an even number. And when I graph f of x equals x squared, right, it looks like this u, right? Now I notice that on the left-hand side, so this side right over here, my end behavior is going up towards positive infinity, right? My right end behavior is going up towards positive infinity, right? So I have the same end behavior on both sides. F of x equals x squared is kind of a special case in the sense that it's going, it's directly symmetrical across, your axis of symmetry. You're not always going to have an axis of symmetry, but yeah, we can just look at the end behaviors and see, are they both going in the same direction? If they are, then we know that our degree is even. Okay, let's look at our when our degree is odd, right? So when our degree is odd, right, instead of the right and left sides having the same behavior, they're actually going to have opposite behaviors. And so let's look at another classic example of what that means. So if I have f of x equals x to the third power, right, if I were to graph this, that's my xy plane, right, then it would look a little something, I'm going to do this in a different color, look a little bit something like this, right? I clearly did not hit those critical points very well, but you get the overall shape, right? And so if you look at the left end behavior, right, you see that it's going down towards negative infinity, but our right end behavior is going up towards positive infinity. And so because our end behaviors on either side are different, we know that this is an odd degree function. So some other things that we can look at in our function, we looked at degree, right? We can also look at our leading coefficient. So when our leading coefficient is positive, and we talked about this when we were looking specifically at quadratics, right? It tells us that as x approaches infinity, f of x also approaches infinity, right? And so another example of this, we can use f of x equals x squared, once again, because that's a positive leading coefficient, right? And so when I graph that, right, as we go further to the right on our x-axis, so as x approaches positive infinity, we notice that our graph continues to go up to positive infinity as well. So let's look at when our leading coefficient is negative, right? So when it's negative, as x approaches infinity, f of x actually approaches negative infinity. So I'm just going to do negative infinity symbol. And so my example of that, I'm going to look at x squared again, but I'm going to look at specifically negative x squared, so I get that negative leading coefficient. And so if you remember back from our quadratics unit, when we were graphing our quadratic with a leading negative coefficient, right, that actually flipped our parabola down. And so we see that as x continues going to the right, our graph, f of x continues going down towards negative infinity. Right, so that's another kind of pattern that we can notice whenever we're given the function of a polynomial, right? In addition, the maximum number of terms in a function is n minus 1, right? Where n is the degree of the polynomial. And when I'm talking about terms, that's actually kind of an informal name of maximums or minimums. So maxima or minima for plural. And generally, the maxima or minima of a function are called the extrema, or the extremes, right? And so your max or min, this is going to be those bumps and curves that you see in your graph when you actually graph it. So when we were talking about intercepts, right, let's actually apply what we know about polynomial shape patterns to what we know about intercepts to kind of intuit what graphs of polynomials should look like. So let's take a look at the graph for the function f of x equals negative x to the third power plus 4x squared plus 3x minus 18. Okay, so we see a few different zeros going on, right? So we see that our first 0 is right over here, and then our next 0 is right over here. But we notice something really interesting with these, right? So when we look at our first 0 over here, we see that our line just passes through the x-axis. But then at this 0 over here, we actually notice that we kind of bounce through, right? So we just touch the x-axis, right? So let's look at each of these zeros, right? So if I'm looking at -2, because I'm just passing through it once, -2 has what we call a multiplicity of 1, right? If I'm looking at x equals 3, that 0, right? I notice that because I bounce back, right, I hit that 0 twice. So 3 is a 0 with multiplicity 2. Okay, so if the multiplicity of a 0 of a polynomial function is even, right, so in this case, something like our x equals 3, 0, right? So if the multiplicity of 0 of a polynomial function is even, the graph of the function touches the x-axis at that 0. So we see that we actually touch the x-axis, but we don't actually go past it, right? And so if the multiplicity is odd, then the graph actually passes through the x-axis at that 0. Right? And we want to look for multiplicity by seeing if we have a bump or a turn at the x-axis, right? Because if we do, then we know that we have multiplicity greater than 1, right? Because we're hitting that 0 multiple times. Another thing that I want to note is that over here, right, if we look at the left end behavior and the right end behavior of this 0, right, another reason why I know that the multiplicity is going to be 2 is because in my left end behavior, I see that I'm going down towards negative infinity, and then over here, I'm going down towards negative infinity, right? They have the same general shape and pattern of our slope on the left-hand side of the 0 and the right-hand side of the 0, right? So because they have the same kind of behavior, I know that this multiplicity has to be an even number, right? Just based on what we talked about in terms of those general shape patterns for polynomials. So let's actually go through a practice problem, right? So the graph to the right is one of the following functions, and we want to identify which function this is, right? So in order to identify which function this is, I want to think about my, where are my x-intercepts in my function? So over here, I see an x-intercept, right? That's at x equals -2, okay? And then over here, that's at x equals 3, right? So because I have x equals -2, if I were to actually kind of reverse the zero product property, I know that my factor would be x plus 2. And then for x equals 3, if I reverse the zero product property, I know that would be like x minus 3. Now I want to determine the multiplicity, right? And so when I look at x equals -2, right, I know that my multiplicity is going to be odd because I'm passing through the x-axis, right? So it's not going to be an even number because, like we talked about before, if we have a multiplicity of an odd number, then we know that we're passing through the x-axis, right? And so that directly corresponds with the exponent of this factor, right? So I know that the exponent for this 0, x equals -2, has to be odd. So I'm going to just write odd over here. I don't know what odd number, but I know it's going to be odd. And then if I look at this 0 over here, right, I see that I just touch my x-axis, right? So because my 0 just touches my x-axis, it has a multiplicity of an even number, right? So I know that that's going to directly correspond with the exponent of that factor, right? So I want to look through my answer choices and see which of them has x plus 2 with an odd exponent and x minus 3 with an even exponent. And so when I look at this, I see this one, right? C, x minus 3 has an even exponent, x plus 2 has an odd exponent. So this looks like it's going to be our answer choice. Let's look at practice 4 with multiplicity, right? So we want to use the graph to state the zeros for each polynomial function. So we want to state the multiplicity of any roots if the multiplicity is 2 or higher. So let's look at this, right? Let's first identify where our roots are. So our roots are over here at x equals 0 and over here at x equals 2. I know this because that's when it passes or touches the x-axis, right? So I have x equals 0 and x equals 2. So when I look at x equals 0 right over here, right, I notice that it kind of just touches the x-axis. So I know that this probably has a multiplicity of 2, right? So this has a multiplicity of 2 because I'm touching the x-axis, right? So it has to be an even number. So it can't be 1, right? Over here, I'm just passing through this 2, so this is probably just going to be multiplicity of 1. Great. All right, let's try our next practice problem. Like our previous practice problems, you can just pause it here if you want to try it on your own, and then press play when you want to go over it. So first things first, we want to identify where are our zeros, right? So our 0 is at x equals -2 and x equals +2, right? So I have x equals -2 and its conjugate x equals +2. Great. Okay, now I want to identify the multiplicity. I see that I'm passing through -2, so because I'm passing through, I know that my multiplicity is going to be odd, and so I know that I'm not really like bouncing back at -2 in any kind of way, so -2 is just going to have a multiplicity of 1. Over here, my multiplicity is going to be even because I see that I'm touching the x-axis, right? Another thing that I want us to kind of see or connect is over here, if let's actually block this out. So if I were to draw a little, right, so if I just block off the left-hand side of this function, I notice that I kind of see a mini parabola, right? So because I see a mini parabola, I know that this should correspond with like my multiplicity, right? And so my multiplicity is going to be 2 because of this, because I see like a mini parabola at x equals 2, right? So let me just actually get rid of that. Oh, I guess I can't get rid of that. Yeah, whatever. Okay, anyway, so this has a multiplicity of 2. And then finally, for our last practice problem, once again, you can pause, but if you're ready to check this, let's check this together. So I get x equals -0.5, x equals 0, and then x equals 0.5, right? I'm right over here for my intercepts. Okay, so I see for all of them, I'm just passing through the x-axis, and so all these are just going to have a multiplicity of 1. God, my handwriting's bad. Anyway, this is the end of the slides for this section of the video. So in our next video, we're going to be handling the next 7-ish, 6-ish slides. So if you have any questions, make sure that you are emailing me, and I'm more than happy to help. Good luck.